Right. No, I'm good. I've got a double coffee.
Alright, so hi everyone. This is Arthur's Master Thesis Defense. This is Inigo from SDU, Associate Professor in SDU Robotics. So we start with the presentations, I guess, and then the Q&As, and then we'll give the evaluations afterwards.
Yeah,
So it's yours.
Thank you, John. So yeah, my name is Arthur. You all know me. Thank you for coming. That's the first thing. Yeah, and today I'm going to speak about my master thesis. It's about implementation, fine-tuning, and evaluation of vision language action models on a real-world manipulation platform. And the focus of the thesis is on explainability, future conditioning, attention. So most of you already know what a VLA is, I'm just going to go quickly through it. So you have kind of a pre-trained VLM, vision language model, that acts as a backbone, and you also have interlit with it an action expert, and that through diffusion generates an action chunk that the robot has to perform. And the input data looks like here on the left. So you have data from different robot embodiments, and you capture, for example, the joint angles of these robots, and also camera feeds from what the robots are seeing.
Yes.
Now, robots have been able to move from A to B for decades, but what is it special about VLAs? So usually in classic robotics you will have multiple modules, such as one that detects shapes, colors, also an algorithm for calibrating the camera, IK, collision avoidance, etc. The good thing about visual language models or foundation robotics models in general is that you can kind of have this one model that understands the scene, and it has this understanding of the physical world that emerges through large-scale training. In this case of VLAs, you just give it a task and an image. And you can see the advantages of each of the approaches highlighted in blue and green. So the classical robotics is transparent, you have a condition and you always know because you programmed it what will happen. It's also very accurate for the design situation. Whereas VLAs are scalable, they can reason thanks to this emergence of the understanding of the world. They are easier to adapt to new scenarios, there's less effort involved in it. So in the case of, just to exemplify it real quick, in our laboratory we kind of have a 5-0 model, which is a specific VLA model. We prompted to do a certain task, and then with the cameras that we have on the robot, the recordings of the joint positions, we can feed them into the robot, into the policy, and then we generate a chunk of actions. A chunk is just a set of a certain amount of actions, and yeah, the robot, the policy acts in the robot. Here we mention as well the advantages of each of the approaches are also the disadvantages of the other approaches, meaning that VLAs, for example, are very scalable, is adapted to new scenarios, but they are not very accurate, and they are really transparent. They usually treated as black boxes, such as many other deep learning models. And these weaknesses have been tried to be approached by different laboratories and different companies. Here you can see kind of a graph plotting the self-proclaimed performance of these models. It is a bit outdated because it's from 2025 in October, so now there's models that are way better than this. But what these models, each iteration try to do is make some kind of improvement in accuracy, either by having some VLM that has better grounding capabilities, or some text progression kind of knowledge. And also this field is quite new. So you can see here a figure from meta-analysis from Moritz Rose, in which it is expected to have plus 1,000 publications on VLAs in 2027. And this raises the question of also, do we have a framework that is consistent for evaluating this robot policies? Currently, the state of the art is having simulation, so with different Libero suits, also Realm and StarGem are quite known in this area. But the problem is that because there's different problems such as overfitting and also kind of not being able to really dissect what is in distribution, out of distribution. There's different iterations of simulations that have been developed every single year. There's not really consistency. Plus, there's a gap between sim to real. So this is something that would be also good to address. So taking this into consideration, we raised the research questions of can we improve the accuracy of VLA models? Maybe not to this 99.9% expected in the industrial settings, but just even marginally so that we can just kind of direct new research kind of directions. And also, can we improve the explainability of VLA models? And this is very important in human-centric environments where these models will interact in very dynamic settings on people. We would like to understand the intention of these policies. And this thing will eventually look into the accuracy, because if you understand what happens in the VLA model, you can further improve it. And this is a final note. Can we maximize the contribution to the community? Well, I need to find the answers to these questions. I think that open source is quite important. I also think that having guides will push the understanding of the community and how to evaluate methods or how to understand them will just push the boundary of research forward. So we go through the method. We set up a laboratory setup for collecting data, for testing, evaluation of VLAs, and this is based on state-of-the-art laboratories, also experience with hackathons. So yeah, it's just kind of a workspace area that is similar to, we try to make it similar to most pre-training available data of VLAs. Also, we try to keep constant background conditions for the visual input. Yeah, and we have different compute units. We consider different accuracy improvement methods such as data augmentations. This is from VLM supervision, task progression feedback, or future task progression. We explored a little bit these areas. We were lucky enough that a lab in Vietnam contacted Professor Tran they developed this method called FOCA that uses also future task progression. And we basically, they needed some help with testing and evaluating the model, and we agreed. We also thought it was a great idea to kind of shed some light on what works and what doesn't work for accuracy improvement. And also we decided that later we could do some explainability analysis on FOCA. Yeah, so this may look super complex, but we'll go in the future further to what this conveys. But this is essentially a base VLA model in which different tokens are added with the purpose of adding this future conditioning to the VLA model. So basically only these two sets of tokens are added, and they are training with different loss functions. The representative explicit tokens are meant to kind of align the current latent representation of the current state with the future representation of object-centric areas. So there's an external model that is trying to kind of predict what is the area of interest, so where the manipulation happens. Yeah, it throws bounding boxes, and then this is encoded to kind of the same latent space as the current state. And then on the other side, we have another set of tokens, the representative implicit tokens, that are trained through contrastive loss to kind of make them closer to the actual trajectory in the future, pull them more far away from what is not the same trajectory or the same episode, practically speaking. This is the VLA model that is the base one. So this builds on top of this. Yeah, I'm not going to go exactly through how the transformer layers and so on work, but this was really important to kind of understand and then implement this book in our pipeline. Yeah. Then we started, our task was to evaluate this model. So we set two tasks. One is just pick up the lab, test it with the red contents, and place it in the smaller lab tested folder to the left. And to the right, we have pick up the light blue container with screws inside it and put them into the bigger gray container. As you see, the prompts are very specific, and this is just with state-of-the-art kind of guidance on how to run these models. Also, these tasks are selected because they give room to a lot of different testing that can be done. For example, here we placed 3 different destructor objects. It will always return picture in the red, but it's also interesting to have objects that are very similar in shape, but of different color. And the bulk material one is more simple, but it also requires to have some awareness of whether the screws are in or out of the cutting. We mentioned that VLAs are important for human-centric environment, therefore we also implemented a safety feature. It's simple, just a checkpoint pre-trained from hiding place, and whenever there's a hand in the frame, the robot stops. Now, for the explainability part, we take inspiration from VLM explainability work, and we do attention plotting, we do attention heat maps, but also attention distribution to different inputs or different tokens that are fed to the transformer. This consists in visual, language, proprioceptive, which is the current state of the robot, and also self, which denotes the different actions within the action track. So if you're predicting 50 actions, that's corresponding to the last one, to the beginning of the set of actions, will also pay attention to the other ones in the same set. And this is also some other technicalities on how the attention plotting is done. Perhaps not super relevant for the presentation, but we'll just to hide. I would say though that because of different padding that is performed by the Pi0 model, some of the heat maps that you will see have some artifacts that don't correspond. So the model is paying attention to areas that don't correspond really to an object of interest, but just to some artifacts that come from padding and other transformer processes that are well known. Another thing that we try to address is this way of evaluating and collecting data. So we think that data should be not only collected to kind of improve the accuracy of the model, to achieve a very good kind of task success rate, but if we want to analyze how something works or how an implementation works, we should probably collect the data with evaluation in mind. So we come up with this not perfect or consistent method for collecting robotic data. And here we just split the data and then we collect these 100 episodes into 40% of episodes that are very similar to each other. These are in distribution, and then 3 sets of 15% episodes of also in distribution but less frequent, 5% of episodes in distribution on one demonstration, so one shot, and then 10% of recovery examples. And then the testing is basically speaking the same kind of frequencies, the same percentages, and in this way we kind of want to have an approximate of what is in distribution, one shot, etc. We will do different evaluations, online and offline. Offline meaning just recorded episodes from the dataset, and online in the live evaluation we will collect all the data so you can later analyze it. And these are the episodes selected for the offline evaluation. So here, based on results, actually, the people from FOCA claim that the results or the method improves over the base Pi0 in all scenarios. With this method of evaluation, we find that is not always the case, although it is also true that there's pitfalls within this data collection method, which has been already improved, but it's not in this work. And we see that correlated here. This is what they claim. So you can see that FOCA is better than Pi0 in kind of all of the data sizes and all of the tasks. We find that this is not actually the case for everything, although we see that some of the statements that they make of FOCA being, for example, better in low data regimes, they hold true, and especially for high accuracy tasks such as lab tested placing. Because there's pitfalls within this method that I can comment on later, we kind of retrieve to their larger, more extensive evaluation, and we try to associate the findings that we do for explainability to these results. Yeah, and here, because I think I'm going out of time, I will really quickly go through the results, because it's not really important showing that foci is better or not, but just the method of evaluating a VLA through attention. Yes, so we can see here, for example, how these drag tokens, which are these additional tokens, they kind of, as for example, we can see here that the attention budget overview across 10 episodes and 4 models. The right? So per episode, visual budget showing the forecast stability of 0 episode dependent variation. This is very kind of nuanced and very deep analysis, and I think I would just move a little bit forward. But there's kind of different patterns. For example, adding these tokens also makes camera preferences in terms of where more attention is paid kind of flourish. So foca always concentrates on one camera, which is the wrist camera, versus Pi0 kind of changes the camera that it pays more attention to quite frequently. Yeah, this is also another metric. So you can see here that this phase profile in terms of how much visual, how much attention is paid to visual tokens versus other tokens, and you can see that in foca, this is quite constant versus in Pi0. At the beginning of the episode, there's not really much attention paid to that the visualization tokens. So at the end either. In terms of language, we see that most attention is paid to kind of this first token of the sentence, and this is quite a known kind of phenomenon in transformers, in which kind of all this attention is dumped to the first token. But other interesting things are, we train the model with 2 tasks, to accomplish 2 tasks, and we see that the words that kind of make, so verbs are the most attended, but also the verbs that are different among 2 tasks are the ones that are mostly attended to, which is also interesting. So you can see that going forward is very much more attended than pick, it's almost 3 times as more. We also have pick here, so pick is common in both, but they are not as much attended as the ones that are different on 2 tasks. There's also correlation between the more budget policy allocates to the visual tokens, the brighter the heat maps are, whereas in foca 40%, the correlation is even stronger in this direction. Yeah, also the foca on the Pi0 transformer architecture has different layers, has 18 in total, and different layers correspond to different layers take the role of doing a different task. We can see that these tokens that are added to foca are mostly used at the end, so close to the prediction. Whereas the beginning of the first layer of the transformer is mostly visual, so it attends like 99% to visual tokens. And there's other interesting analysis that the camera. And then offline validation. So online, this is timeline. So this is 176 closed loop inference runs. It takes a lot of time to do them, but the main point is that they confirm the findings found in the offline evaluation, meaning that the observations that we make are architecture invariant and not just being trained artifacts. Average get this signal timeline going into the analysis part. So here we can see that the cross-episode analysis demonstrates that the VLA internal processing is way more structured than a black box. There's layer specialization that is consistent for different modes of evaluation. A1, the first layer in the primary language layer, having proprioceptive specialist, etc. and then having budget allocation, which reflects strategy. So for example, focal changes quite often from purple to self. Anti-zero is found out visual to self. Self being self-attention to actions. Right. That was like some videos here. What was actually interesting to show? Yeah, so you can see here, this is the first layer. You can see almost 100% of attention to visual. And on the right, you can see the last layer, in which most of the attention goes to self. Now, online versus offline evaluation. This is a point that I mentioned before. The results are consistent among both types of evaluation, which basically means that we can have a method if we prove that attention is causal. It's just not so straightforward. You could have a method that is good for evaluating policies without going into simulation or going into real-life evaluations, because we saw that real-life evaluations and offline evaluations show similar results in terms of attention. So you could just take the original data set and evaluate a model without having to invest more time and effort. Yeah, this is also another trend. We see that the first actions of the 50 action chunk that we used to train pay a lot of attention to proprioceptive state, little attention to themselves, whereas the last, this is action 1, 3, 10, 20, 30, 40, 39. And we can see that the last one pays the most attention to other actions within the sequence.
Okay, good sign in. Then what?
So with this method, also the point that I mentioned before, we try to kind of come up with a way of collecting data so that then we can evaluate through attention how policy performs. And we see that there's claims from the FOCA team that are made in evaluation of, with simulation and real life that are supported with this attention mechanism and that's it. Right. So this is just also like some information how the data was logged. And I think this is also especially useful because you can leverage a lot of the state-of-the-art LLMs and VLMs to make an analysis on how a VLA acts internally. Of course, then in the future work I will mention this could be way more precise. But the main idea is this method. And also as a final thing, just some pipeline deployment observations. It is possible to apply different smoothing mechanisms to the motion. We saw a lot of jitter when doing inference at 40 Hz or 30 Hz. And kind of the most simple approach was just to decrease kind of the control frequency to achieve more smooth motion. Also make sure your cameras have an independent USB controller, otherwise it will collect data sets and there will be shit. And yeah, also this background consistency was important for dividing in distribution, out distribution and so on. And also collect as much data as possible. We collected even depth data out of like intention data and then all the rhythm use. I think it can allow very important future work. What's interesting finding the hand safety mechanism ends up quite useful for accelerating quality testing. So we can just quickly change the setup without stopping the policy. The robot stops and then it goes again into evaluation. As a final conclusion, we kind of show that explainability helps to understand accuracy implementations and it can kind of intended to improve the accuracy. And we also do so by kind of helping kind of the community with different articles and different YouTube videos. That's long data sets that hope to kind of push a little bit the research forward. future work. It could be quite interesting, for example, to use this attention kind of mechanisms with reinforcement learning. So, for example, if we prove that it is causal, because although we see that the kind of attention is correlated, the attention distribution is correlated with results, it's not necessarily causal. And if we prove that it's causal, this could be very useful for reinforcement learning, because we could, for example, check that if a policy attends to the right object all the time, it will have a higher but a more kind of dense reward signal than just a binary failure class. And you have also VLM assisted attention pattern recognition. So the distribution was automated, but seeing where a model attends within an image is way more complicated to achieve at scale. So that could be also interesting to explore. And of course, like prove this causal relationship by updating, for example, the existence of some tokens and seeing if models still perform as well. Yeah, I hope I didn't go much over time. Thank you.